Hello guys, welcome back to Maths and Physics Blog. Today we're going to go over the start of our Abstract Algebra series. So our first video here is an overview of mathematical set notation. So this is probably quite a basic mathematical video, but it's kind of the underlying things you need to know before we get into Abstract Algebra. So the basics. We know that a set, or you might know, a set is made up of elements or objects. So that could be anything from numbers, 1, 2, 3, ABC, whatever. It could just be countries, it could be whatever. Just a set made of elements. And that's what it says. So if one of these elements, A, is in the set, then we can denote it by this symbol here. So A is in the set S. That's what that symbol means. So if we have a set with no elements in it, then we call this the empty set. And it's denoted by this circle with a line through it, meaning the empty set. Now, every single empty set is actually equivalent to each other, no matter if you have numbers or letters or anything. If it's empty, obviously there won't be numbers in it, but let's say you take them out, then they're equivalent to each other. Now, there are different ways to describe sets. We can describe one using the properties, say the set of all even numbers or the set of countries in the EU. We can do it by listing it in these squiggly brackets, for example, 1, 2, 15, 34. Or we can also describe it sort of with this property, which kind of combines both of them. You have the squiggly brackets x and then a condition p of x, which means the set of all x such that the statement p of x is about x is true. Another thing you might encounter with is a well-defined set. So a set is called well-defined, meaning that we have a set S and some object A, and we know that A is definitely in S. We're not like, if we're a bit unsure, then it's not well-defined. So if A is definitely not in S, then we have this symbol here, and if it is, then we have this symbol here. So some commonly used sets, you probably have encountered these before. We have the set of all natural numbers, 1, 2, 3, all the way to infinity. We have the set of all integers, which are your minus and your positive whole numbers. Then we have the set of all rational numbers, so that's any number that can be expressed as a fraction. With the set of all real numbers, which is kind of most things you'll encounter in modern days, so they're rational numbers, irrational numbers, everything above comes into real numbers. And then we have a set of complex numbers, which brings in imaginary numbers and stuff you can't actually physically see. But we'll get onto complex numbers later on in the series. Subsets. So these are quite important for abstract algebra. So a set B is a subset of A, which is denoted by this symbol here, if every element of B is in A. So they have the symbol here, which means, let's say you have a set A, which is 1, 2, 3, 4, and then you have a set B, 1, 2. Then B is a subset of A because 1 and 2 are both in B and in A. But let's say you have a subset B of A, but the B and A are not equal, that they don't have the exact same elements, then we can actually get rid of that line underneath and say that B is a full subset of A. If A is any set, then we can say that A is in proper subset of A. So that means that it is equal to each other. And then any other subset of A is called a proper subset of A, which means that it's actually not equal to A as well. It's definitely just a subset. An example of this is, say, let S equal 1, 2, 3. Then S has a total of 8 subsets. So if you break this up, we have the empty set. We have 1, we have 2, we have 3. We have 1, 2, we have 1, 3. We have 2, 3, and then we have the set 1, 2, 3. So you can, I hope that makes sense, breaking it up into all the different subsets. Moving on, we have the Cartesian Products sets. So this is quite quite useful. Sometimes you won't see it, sometimes you will. So let's say we take two sets, and then the Cartesian product is given by this value here, where we get a bracket with an element from set A and element from set B for all of them. So it goes through. The example is quite easy. It's easy if you read the example than the definition, I believe. So if you have the set A, which equals to 1, 2, 3, and B, which equals to 3 or 4, then the Cartesian product of A and B is shown at the bottom, where you take the first element of A and the first element of B, you take the first element of A and the second element, and the second element of A and the first element of B, and so on. So you kind of get a combination of all the different elements together of the two sets. Relationships. So relations between sets. The definition of a relation between sets is the subset of this fancy R of A and B. We read that A and B in this bracket is in R as A is related to B, and then we write a fancy RB for a relation. An equality relation is actually quite similar. It's essentially one where they're equal to each other, where two sets are equal. So it's defined by the equal sign that we all know, and essentially it's a way of testing if two sets are similar. So for any x in some random set S, we have x equals x, but let's say x and y are different elements, then xy is definitely not equal, and then we write x is not equal to y. Apologies. Partitions and equivalence relations. So we have sets, and let's say we have multiple different sets. We say that sets are said to be disjoint if two of them have no element in common, so there's no overlap of elements. So you can have 1, 2, 3, and you can have 4 and 5. Two different sets, nothing overlaps, so they are disjoint. A partition of a set is a collection of non-empty subsets of S, such that every element of S is in exactly one of those subsets. And then these subsets are called cells. So at the moment I'm just kind of throwing definitions at you. You can apply them, but you kind of just need to understand what the words mean more than actually applying them. Moving on, we have an equivalence relation, which is kind of what I mentioned previously. But we say equivalence relation, this is the way we test it, has to satisfy all these three properties. So we have a reflexive, so x is related to itself. We have symmetric, so that if x is related to y, then we must have y equals related to x. And then we have transitive, which means if x is related to y and y is related to z, then x must be related to z. If none of them properties, let's say all of them properties are true, then we have an equivalence relation. If one's wrong, then we don't have an equivalence relation at all. So all of them need to be true for the equivalence relation to work. Thank you guys for watching. Make sure you carry on this series if you want to see more content, examples and proof. I hope you enjoyed this video. Make sure you hit like, subscribe, and I'll see you guys in a little bit. Goodbye.